Just to remind you, lecture is canceled on Friday. We don't have lecture this Friday, and then Monday is also a holiday, so you have a very long weekend. This is lecture 14, and today we're going to be talking about the stars. So we're going to be talking about stars that aren't the sun, how the sun fits into our general picture of the spectrum of different types of stars we have in the universe. And I'll talk a little bit about what we know about these stars and how we were able to put some of these things together. Now, it's going to be a very broad brush thing, but just to give you a taste of what we know about the stars. And again, if this were an astronomy course, we'd spend all kinds of time on the stars, but this is a cosmology course, so we're sort of leapfrogging over them. We're using them, and we need to talk about them a little bit, but then we're going to leapfrog into the greater universe. Right? Okay, so this picture is a beautiful picture of the night sky taken over Yosemite Valley. And there is a really famous constellation here in this sky. Does anyone see it? Yes. It's not Orion. It's even more famous than Orion. Yeah. It's the Big Dipper. It's the one that even I can pick out the Big Dipper. There's the Big Dipper. And this thing over here, that's Venus. So that's not a star. Now, the thing about it is, I wanted to use this as a jumping off point because looking at the night sky, a lot of us have seen a beautiful night sky like this, and we can pick out the Big Dipper. If we can't pick out anything else, a lot of times we can pick out the Big Dipper. But we actually know a lot about each of the stars in the Big Dipper. And something that you usually don't think about, right? Because when you see something like this, you think about the Big Dipper as being projected, like they're all in a line. Okay? We think of this as like a two-dimensional thing, but that's not true. We now know how far away those stars are that make up the Big Dipper, and they're actually vastly separated. They just project along that distance. They don't really make a three-dimensional coherent structure at all. They just sort of look to be that way. We also know quite a bit about every star. So like, for example, this one's called Mizar. This one here. It's 80 light years away. It's blue-white, and what I mean by blue-white is that's sort of the color of its spectrum. You know, when we're talking about black-body radiation, it's sort of bluish. And because it's a little bit bluish, that means it's hot. And in fact, it's hotter than the sun, which is more sort of yellow-greenish. It's 9,000 degrees, where the sun is more like 6,000, 5,000 degrees. So this thing is hotter than the sun. And actually, we know now that it's actually a pair of binary stars. It's not even one star. It's two pairs of binaries. So in total, it's 4 stars. The brightest one being this 9,000 degree one. Okay, just a fact, but it's sort of amazing we know that, right? I mean, we know this thing is 80 light years away, etc. Here's another one, Dubhe. So this is Arabic for the bear, right up there. It's 120 light years away. So it's actually much farther away than this guy down here, and they look to be about the same brightness to your eye. If that's the case, right, this thing is much farther away, it must be intrinsically really bright. And actually it is, right? So it's actually the second brightest star in the Big Dipper, but it's the most distant star in the Big Dipper. In fact, it's a little bit unusual because it's sort of a dying star. It's on its way out on the scheme of things. It's actually fusing helium in its core and not fusing hydrogen. And it's going to die soon, give or take 500 million years. Okay, so that's soon in an astronomical sense. And it's classified as a giant star, and we'll talk a bit about that. And the thing is that's kind of interesting is even though it's so bright, right? It's actually cool. So it's a little bit cooler than the sun. The reason why it's so bright is because it's big. It's physically very big. And so it's so big that it's putting off a lot of light. And so this gives you an example of there's this star down here we were talking about before is on the main sequence. It's a main sequence star. It's a typical star like the sun, and we'll talk more about what that means. Whereas this star up here is not on the main sequence. It's getting ready to die. It's a giant star, and it's not fusing hydrogen anymore. It's fusing helium. Here's another famous constellation, and it is Orion. Very good. It's Orion the Hunter. This is another one. If you're going to get two constellations right in the night sky, it's usually going to be the Big Dipper and Orion. Orion is a pretty easy one to see. And you can see this by eye. What I want to talk about specifically is this thing up here. To your left, in the northern hemisphere, if you look up and see Orion at night, you'll notice that this star up here to the upper left, in sort of his armpit, is sort of red. And you can see it red by eye. Now you can see Orion tonight. If you go out tonight and look up at the night sky, you can see Orion. Okay? And you can see by eye that there's one star that looks red. Has anyone seen this? Yeah, there's one star that looks kind of red. And you need to get this down because you can impress your friends with this if you're ever out camping or something. You can tell them something about this star. This star, it's pretty easy to pick out, right? You can pick out Orion. You can train yourself to pick that out. Even I can pick it out. And you can learn this star, which is called Betelgeuse. So that's a fun name to say. You can remember that too. And it's red. Why is it red? Betelgeuse is a red supergiant. It's a gigantic star. It's super duper big. If this was the sun here, and that's the orbit of Mars, that's the orbit of Jupiter, the physical size of Betelgeuse is something like this. It's certainly bigger than the orbit of Mars. So if you replace the sun with Betelgeuse, we would be inside of it. That's how big it is. It's huge. Okay? And for that reason, it's crazy bright. It's 10,000 times brighter than the sun because its surface area that it's shining from is just ridiculously big. So that's kind of crazy. It also varies, it turns out. It's actually shrinking and growing with time. And it changes its brightness by about a factor of 2. So in recorded history, right now it's about the 8th brightest star in the sky. There's times in recorded history where it's one of the brightest, 1 or 2 in the sky. And then it gets a little bit dimmer after that. So it's a pretty crazy star. It's very interesting. It is distinctly not on the main sequence. That means it's also about to die. And when it dies, it might do something really cool, and we'll return to that at the end. Now, how is it that we know how intrinsically bright Betelgeuse is? And so I want to use this as a jumping off point from there. How is it that we know how bright this thing is? How do we know that it's 100,000 times more luminous than the sun? Because just by looking at it, it could be anything, right? I mean, something that's as bright as Betelgeuse in the sky could just be an airplane, right? You'll see an airplane fly by, and it has a light that looks brighter than the star Betelgeuse. So it depends on how far away the star is, right, for us to know how intrinsically bright it is. So I want to use this as a jumping off point to talk about distances and luminosities of stars. So one thing we could do, a reasonable place to start, if we wanted to look at the stars in the sky and ask how far away they were, we could start with a really simple assumption. We know this is wrong, but this could be at least a reasonable starting point. You could say, look, we think that all those stars in the sky are just suns. They're just distant suns. And so if we assume they're all as bright as the sun, we can roughly guesstimate how far away they are. And in fact, that's what astronomers did sort of a long time ago before they had more precise ways of measuring the distances of the stars. They just made simple assumptions like this and kind of worked out roughly how far away the stars needed to be. Now, this could work okay, because I mean, imagine you have a light bulb, right? It's a 100-watt light bulb. If it's right in your face, you know it's really close because it looks really bright. But as I take that light bulb away from you, it gets dimmer and dimmer and dimmer. And if you knew how intrinsically bright that light bulb was, and you saw how bright it appeared to your eye, you could guess how far away it was, right? So imagine we're out in a really dark field, no lights at all, except for me and my light bulb, and I go away from you some distance, you could guess, oh, he's 100 yards away, or something like that, depending on how bright that light bulb looked to your eye. So you could just imagine qualitatively doing that, right? Now, in practice, that doesn't work, as I mentioned already, because not all stars are the same light bulb. Some light bulbs, it would be like me having a trick light bulb that was actually 100 times brighter than a 100-watt light bulb and taking it out and have you guess, right? It wouldn't work so well. So how do we do a little bit better than that? Then we got to think a bit about the full complexity of how bright something is to you. So this is an equation that characterizes the apparent brightness of a source. So B is for brightness. Now, first let's just think a little bit about what that is. Like, what does your eye perceive as brightness? What's actually going on, you remember when we talked about telescopes, we compared that to the eye. Your eye has a hole, okay, where light comes in that hole. And the number of photons that get in that hole per unit time is something like how bright you see it. how bright you see a source being. If a whole bunch of photons, a whole bunch of light is coming through that little hole, your brain says, oh, that's very bright. But if only a few photons are coming through that little hole per unit time, your brain says, oh, that's very dim, I can't see much. Okay? Now, your pupil has a given diameter. So you can think about that as how much light is coming in per unit area of your eye. So that's sort of what this characterizes. This brightness is the luminosity, where luminosity is energy per second being pumped out of the light source from the light bulb. So that could be 100 watts. Okay? And divided by this is actually an area, 4 pi r squared, where r is the distance to that light source. And the first thing I just want to emphasize is the units of this are power, watts, say, per unit area. So watts per meter squared, for example, is a unit of brightness, intensity. So are there questions about that basic sort of explanation of what brightness is? It's power, but now per unit area. And you can see in the equation, right, if R is the distance, imagine it's a light bulb that's putting out 100 watts. This distance is the distance to the light bulb. So if you're up close to the light bulb and R is small, then that brightness is big. But as you back away from the light bulb, R gets bigger, it's in the denominator, so the brightness falls off. And it falls off in a very specific way. It falls off like the distance squared. So if I take my eye twice as far away from the light bulb, it looks 4 times as dim. There questions about that? Now, what's up with the 4 pi? Is this magic? Like where does the 4 pi come from and why is it r squared? What's happening? Well, it turns out there's actually a really simple reason why this is the equation. Okay? This 4 pi r squared, it turns out, is the surface area of a sphere of radius r. So if I have a sphere which got 1 meter radius, its surface area is 4 pi meters squared. Now, if you have a light source that's spitting out a given amount of energy, right? Imagine snapshot 1, it spits out 1,000 photons. And you measure how many photons are coming across a very small sphere, right around that, it would be 1,000 in total. But now imagine tracking those photons until they're twice as far away. Now that same number of 1,000 photons is spread out over a sphere that has a radius that's twice as big, and therefore an area that's 4 times as big. And so they're diluted as they go out. So the total amount of power that's escaping this imaginary sphere is the same, but the area over which that power is spread out is growing and growing and growing like the radius squared, because the surface area of that imaginary sphere is growing like the radius squared. So it's not, any surprise really that this equation has a 4 pi r squared in it, because that is the surface area of a sphere. Okay, are there questions about this? So this is a fundamental thing. The brightness of an object falls off like the distance squared in a very, very precise way that's very well understood. So imagine, for example, that you had 2 stars of exactly the same luminosity. So they were both 10 to the 26 watts or something. But one appears to be 100 times dimmer by eye than the other. 100 times dimmer. That is, with a brightness that's 100 times smaller. How much farther away is the dim star? Sorry? You raise your hand? I can't see you. 10 times. Why 10 times? Because it goes like squared. So if it's 10 times farther away, that light is spread out by 10 times squared less. Okay, that becomes 100. So if you're 100 times dimmer, you must be 10 times farther away. Okay, so this is the very extremely elaborate way of working that out. Okay, I told you that the brightness of one star is 100 times smaller than the brightness of this. So brightness of star 2 is 1 over 100 times the brightness of star 1. Okay? Now I know from this equation that the luminosity of a star is equal to 4 pi r squared times its brightness. So that means, and I know the luminosities of both stars are the same. So I know the luminosity of the star is 4 pi r1 squared times brightness 1. Luminosity of the other star is 4 pi r2 squared times brightness 2. But I know these two are equal. So I can then set them equal to each other, and I find that r1 squared equals r2 squared divided by 100. I take the square root of both sides. That means r1 is a tenth of r2. So it's 10 times farther, r2 is 10 times farther away. So this is the sort of explicit, equation way of solving that. Or you can just think to yourself, well, it falls off like the distance squared, and it's 100 times dimmer. So in order to get a factor of 100 with something squared, it must be 10 squared. So 10 times farther away. Okay, so if something is, say, 4 times dimmer, how many times farther away is it? If it's 4 times dimmer, I don't want you. You're the ringer. I want someone else. Someone else answer. So if it's 4 times dimmer, how many times farther away is it? Who thinks 30? Okay, good. Who thinks 2? Good, okay. If you're having trouble with that, okay, think about it. Take some time after lecture to go through this and think about it on your own. If you're still having trouble with it, come to office hours and we'll talk about it. Okay. Okay. Now, the trick is, okay, we're looking at a star. We can measure how intrinsically bright it looks to our eye. That's B. What we'd really like to know is how bright is it? What's its absolute luminosity compared to, say, the sun? But in order to know that, right, we can measure this thing. We want to know this thing. We must figure out what R is. We need to figure out the distance to the stars. So figuring out the absolute distances to stars was a huge, huge kind of roadblock in astronomy for a long time. Because it turns out that's a pretty hard thing to measure. Because, you just see these stars, like how do you know how far away they are, right? How do you know whether it's an airplane or a distant star, right? There's a couple different ways that you can know. Like, for example, with an airplane, how do you know something's an airplane in the night sky compared to a star? It moves faster. Yeah, it moves. Exactly, it moves. So that means it's probably closer than the stars, right? It's not like the airplane is actually moving faster than the stars physically. It's not. It's just that the stars are so far away that their movement is imperceptible. It's just that the airplane's nearby, so it whizzes by, and the stars are so far away you don't see them shift in angular space. That effect is something we talked about before. That's called parallax. And in fact, we can use a technique known as measuring angular parallax to precisely measure the distances to the stars. Now, I'm not going to go through this now because that's the subject of your rocket mix module that's going to be assigned tomorrow night. So you're going to go through this module, and when you finish it, you will be masters of parallax. I promise you, you'll get it. Okay? Point being, we have techniques for figuring out the distances to stars, and it relies on this trick of parallax that we've talked a little bit about before. The Earth is going around the sun, and we use that as a baseline for basically doing triangulation to stars to figure out their distances. Okay, so roughly we learn about the stars because we have techniques for measuring their distances. We can measure how intrinsically bright they are, and then we can start putting together a physical picture about the vast array of different types of stars that exist out there in the universe. So what I want to do now is give you a bit of an overview of what we've managed to put together about all those stars that we see up in the night sky and that you actually can't even see because they're so far away that we've studied with telescopes. Okay. Stars shine. Why do stars shine? Simple answer, stars shine because they're hot. Okay? Anything that's got a temperature shines. And stars shine because they have a temperature. And very roughly, stars shine like a black body. This black body radiation that we talked about before, they emit energy. The color of that light depends on the temperature of the object. And specifically, the surfaces of stars are the things that have this temperature that we use to characterize stellar temperatures. Okay? So starlight is basically internal heat that's leaking through the surface of the star. And this thing we call luminosity is the rate of energy loss. joules per second, or watts, just energy per unit time. It's the rate with which energy is leaking out of the star. That's what we see as they're shining. Now, in order to stay hot, stars have to keep making new energy. If they weren't making new energy, they would just fade out, right? Because they're spitting energy out all the time. So in order to maintain their brightness, they have to create energy, or otherwise they just cool off and fade out. The way they do that is fusion. So we've talked about this before. So for example, most stars that are sort of characterized as normal or main sequence stars, are fusing 4 hydrogen nuclei into 1 helium nucleus. If you take 4 protons, they actually weigh slightly more than 1 helium nucleus. The leftover is 0.007 kilograms. So if you take 1 kilogram of hydrogen, it would fuse into 0.993 kilograms of helium. The leftover 0.007 kilograms, 7 grams, is converted into energy. 7 grams would create this much energy in joules. That's enough energy to power your home for 20,000 years. So this is a tremendous amount of energy from converting hydrogen to helium. Right? We've heard about this kind of stuff before. But not all stars are the same. Okay, so there's sort of a vast array of different types of stars. And one of the things we've learned that if you take stars and you plot their luminosity, and again, this is something we can now measure, how intrinsically bright they are compared to the sun, and plot it on this axis. First is their surface temperature on this axis. Now, one is the sun here, right? So it lives somewhere along this line. And it also is a G star. The sun is right here. So the sun has luminosity of 1 sun and a temperature of about 6,000 degrees. Okay, so that's where the sun is. Something up here is 100 times more luminous than the sun. Something down here is a lot dimmer than the sun. And across here, again, is the temperature in Kelvin. So this is 6,000 degrees, 10,000, 30,000. Down here is only 3,000. Okay. How do we know the temperature again? How do we know the temperature of a star? How could we figure that out? Yes? Sorry? Luminosity? No. It's not exactly luminosity. Yeah? The emission and absorption spectrum? No, it's not the emission and absorption spectrum. You're getting close, though. It has something to do with the spectrum. I actually have already talked about it in this lecture. How do we how do we figure out the temperature of an object that's glowing? Yeah?
Measuring the wavelength.
Yes, you measure the wavelength spectrum that it's emitting. Okay? And generally things that have a temperature glow with a certain spectrum. That's called a black body spectrum. Hotter objects glow in shorter wavelength light. Hotter objects are bluer. Cooler objects are redder in the emission spectrum. And so just by taking the light from a star, spreading it out over a prism, and measuring how much light's coming out in each wavelength, and roughly figuring out the color of the star, we can figure out what the temperature is. Okay, the sun is yellowish because its temperature is 6,000 degrees. Anything that's glowing like a black body at roughly 6,000 degrees will glow with a color that looks like the sun's color. It will look yellowish. Things that are glowing hotter than that will be like blue hot. Okay, they'll glow with more of their light coming out at the shorter wavelengths, blue wavelengths. Things that are glowing at sort of a few thousand degrees will be glowing in the infrared. Okay? We are also glowing, right? We have spectra. But our black body spectra are those that are associated with something that's glowing at a temperature of about 98.6 degrees Fahrenheit. And that's in the infrared. Okay? Is that clear? The point is, we can measure this. It's amazing, actually. We can measure the temperatures of stars by taking their spectra, plotting them and comparing them to a black body radiation spectrum, and then back out what the surface temperature is. So even though we've never traveled to Betelgeuse and stuck a thermometer in it, we know how hot it is, right? Okay, and we know the luminosities because we can measure their apparent brightnesses, and we can also measure their distances through this thing, parallax. Right, are we good on that? So the point is we can measure both of these numbers, and we can just say, well, where do stars sit? And the amazing thing is, most stars line up along this band right here, such that the hotter stars are more luminous and the cooler stars are more dim. This band is called the main sequence. That's just its name. Now there's other pockets of stars though. They don't all sit on the main sequence. There are some stars that kind of poke out here, and these are called giants. And there's other stars that kind of sit way down here, and these are called white dwarfs. Okay, and I'll talk a bit about, and the ones that are really even brighter than that are called supergiants, way up here. Broadly speaking, the stars that are down here, these white dwarfs, these stars are dead. Those are dead stars. The stars along here are sort of in the prime of their life on the main sequence. And the stars that are up here are going out with a great gasp. These giant stars are dying. They die by swelling up and getting really bright, and then they die, and most of them will then drop back down and become white dwarfs. Now, stars that are sort of normal, that are living along the main sequence, are in equilibrium. They're in a very steady state where gravity is pushing them in. They have a lot of mass, and gravity wants to crush them down. But because gravity is pushing so hard in the middle, they've got really high pressure and really high temperature, and they're fusing. They're fusing hydrogen and helium, and this is generating energy and heat, and that's puffing them back out to create pressure. So there's an equilibrium with gravity pushing in and the pressure generated by nuclear fusion pushing out, and there's a steady state. Okay? The reason why it's steady is if you press more, if you pressed harder, you would create more nuclear fusion, and it would get hotter and resist that pressure and resist that crushing gravity and puff back out. Okay, so if you squeeze it more, it'll just get hotter and puff back out. Or if it gets hotter in the middle because there's too much fusion and begins to puff, then the gravity will drop. It will no longer be hot enough in the middle to fuse, and that puffing will go away and it will shrink back down again. So it's sort of this equilibrium configuration that stars find themselves in, and it becomes very steady. So stars that are on the main sequence kind of shine at a pretty steady luminosity, and they're sort of constant sources of energy like our sun, which is basically shining at a constant rate and has been doing so more or less for billions of years. Stars that are on the main sequence follow very simple scaling laws. That is, the hotter the star, the brighter the star. Also, the hotter the star, the shorter its life. Turns out hotter stars, more massive stars, more luminous stars, burn up their fuel faster and die sooner. Hotter stars are also more massive if you're along the main sequence. In fact, the luminosity of a star goes like the mass of the star to the 4th power. So if you take a star and make it 10 times the mass of the sun, it will be 10,000 times brighter than the sun. So it's a very, very strong function of the mass when something's to the 4th power. So what's plotted here is the mass of the star compared to the luminosity of the star, and it's just a very tight and very steep relation. The sun sits here, Betelgeuse would sit like up here. And little dim stars would live down here. Now I mentioned this before, but big stars basically live fast and die young, and little stars are extremely efficient and they burn for a very long time. And you can think of that a little bit like cool stars or low mass stars are like subcompacts, right? They can go for a real long time. Even though they're small, they're very efficient. And even though they have less fuel in their tank, they can just keep going for a very long time because they're very efficient at converting their hydrogen into helium and just burning for a long time. Whereas really big stars are more like Hummers. They can use a lot of energy and they have a really big gas tank, but they're not going to go very far compared to the little thing. Okay. So these stars, actually, there are some stars that are less massive than the sun can live many, many, many times the age of the universe. The sun's going to live about 10 billion years in total. And a lot of the big stars will live, there are big stars that will live 1,000,000 years and then die. And that's a very short amount of time, turns out. Okay, so, however, eventually, all good things must end, and stars are turning hydrogen and helium, and eventually they run out of hydrogen. So they run out of this fuel. And if the star is fairly low mass, what happens is there's not enough energy, so there's not enough pressure, the temperatures aren't high enough to get fusion energy out of squeezing helium. And so what happens is the helium basically it acts like ash. So imagine you're feeding a fire by shoving logs in your chimney, in your fireplace, right? But eventually you burn up so many logs in your fireplace that it's just all ash. So you're not going to be able to make a fire anymore. There's no more fuel. It's just the ash. And so eventually stars generate this sort of helium ash in their cores. And when that happens, the process changes. And it's no longer in this equilibrium state. And the star, the star changes its next step. And what exactly happens next depends on the mass of the star. Now for low mass stars like the sun, what happens is most of its life it just bops along on the main sequence, converting hydrogen to helium. But then it burns up all its hydrogen in its core, and it no longer can do this. And what happens is the outer parts of the star start to fuse a little bit and get puffed up. And it starts to puff itself up into this giant thing called a red giant. And eventually, though, these things don't stay red giants all that long in the scheme of things, and the whole system becomes unstable, and it sheds its outer envelope of gas and leaves behind a little core that's called a white dwarf. So what happens is the star is burning along in the main sequence, but after, say, 10 billion years, it runs out of hydrogen in its core, turns into ash, the whole thing puffs up and becomes a red giant. Okay, when the sun becomes a red giant, its outer envelope will sort of touch the Earth. It will get really big. And that'll happen in about 4 or 5 billion years. So get ready for that. And then after that, it becomes planetary nebulae. Okay? And those things are really pretty. It turns out that some of the prettiest things you can take images of are these planetary nebulae. That's a really bad name. They have nothing to do with planets. They're just called planetary nebulae. Astronomy naming conventions are just stupid. But talk about that another time. But anyway, what's left over, at the core they end up with this sort of very dense thing that's called a white dwarf. And they shed the outer envelope of the star, and it's very, very pretty. The gas has all kinds of different elements in it, and it can be very beautiful for a while. And after this core fades away, it just becomes a white dwarf and settles off down here. And those white dwarfs just cool off and can last for a very long time. So a white dwarf that's left over from a star like the sun will be about the size of the Earth. Okay? They are no longer fusing elements, so they're not creating energy by nuclear fusion. And they just get cold. They glow like a black body, and they just keep cooling off because they're spinning energy out. They have no new way of making energy, and they just cool off and fade out. So these white dwarfs are just left. They're remnants. They're dead stars that then just float around the galaxy that just last basically forever. Now, as I mentioned before, how long the star will last until it sort of dies depends on the mass of the star. So a star like the sun will last in total about 10 billion years. So we're about halfway through. The sun's about halfway through its life. A star that's 10 times the mass of the sun will only live 10 million years. Now, that's really a short amount of time. Okay? So if you think about it like, say, on Earth, had the sun been one of these giant stars, right, there would have never been life on Earth. Certainly would have never been complex life on Earth, right? I mean, it took billions of years for anything, marginally complex to evolve on Earth. So thinking of allowing that to happen in 10 million years is hard to imagine. So stars that sort of don't live very long are probably not going to be that conducive to habitable planets like the Earth. However, if the star was really dim, it could last a really long time. So for example, if it's a tenth the mass of the sun, it would last 10,000 gigayears. So that's many, many, many times the age of the universe. So stars that are low mass will just keep shining for a really, really long time. Okay, now higher mass stars, something else can happen. Different things can happen. If the star is, it turns out if the star is really high mass, more than 8 times the mass of the sun, it will not turn into a white dwarf. But something much more spectacular happens. Betelgeuse is one of these stars. So Betelgeuse is much more massive than the sun. It's so much more massive than the sun that something different is going to happen to Betelgeuse. It won't die as a white dwarf, but it's going to explode. So what happens with stars like this is they're so massive, they get so much pressure in their core that they can actually fuse that helium. So while the helium is sort of like ash in a star like the sun, because it's just not hot enough to make fusion happen with helium in the sun, if the star is really heavy, really massive, it can actually start fusing helium into heavier elements. And so if you remember what happened in this fusion energy chart, you can actually take light elements, even things like helium, and fuse it into even heavier elements and get energy out. So if you have enough pressure, you can begin to march up this table here and get all the way to iron and still release energy. So that's basically what happens at the cores of massive stars. They start fusing helium into heavy elements. Eventually, they take helium and fuse it to carbon and oxygen. The carbon can get fused to neon and magnesium. That happens over like 1,000 years. And then over the next 3 years in the heart of the star, neon can get made into oxygen and magnesium. The oxygen then can get fused into silicon and other heavier elements. And then finally, this silicon can get fused into iron and nickel. So it fuses all the way up to iron. Now, this, turns out, becomes inert. It doesn't matter how much you squeeze on it, you cannot get energy out of fusing iron. Because of this thing that I reminded you of before, iron is just this special element that it turns out if you fuse iron, it actually takes energy to fuse it. You don't get energy out. And so because suddenly, so what happens is in this star right here, it's very heavy. It starts fusing helium into the heavier and heavier elements. Those heavier elements begin to fuse. It's getting hotter and hotter and denser and denser and denser until finally you squeeze in to make this ball of iron. Now, as soon as you have this core of iron, you can no longer fuse and generate energy. So you've got this massive star around you that's being held up by this tremendous pressure you're generating from fusing elements together. And suddenly you can't fuse elements together anymore. So it shuts off. All the pressure shuts off. There's nothing holding the rest of the star up. And it's like it let go. It's let go. It lets go. Right? So it's holding it up with all of its fusion energy. It no longer can generate fusion energy, so it just lets it go. So the whole star just collapses onto this iron core, and there's a tremendous bounce, a tremendous explosion, and that's a supernovae. And so you'll see this happen. There are surveys going on right now where you're just monitoring galaxies, and you'll see some region in a galaxy that looks kind of inert, then you come back the next day, and boom, it gets crazy bright. So there are stars exploding all the time for this reason. So that's called a supernovae. Okay? When that happens, it sheds all those heavy elements that it's been fusing in the heart of these stars, right? You start all that carbon and oxygen and silicate that's been building up in these stars now gets released back to the universe in this massive explosion. And it turns out carbon, oxygen, and all those elements are key elements for making planets like ours and life like ours. So because of these supernova explosions, they release these heavy, complex elements back into the galaxy, which are then incorporated into the next generation of stars, that then become essential for building things like us. Okay? And so if you've heard the phrase, "we are all star stuff," this is what's meant by that. We're made out of the stuff that's blown out of supernovae like this. Literally. This stuff was not created in the Big Bang. It's created in explosions like this. Supernovae are crazy bright. A supernova can be 10 times brighter than an entire galaxy, briefly. So the billions of stars in a galaxy are outshone by a single supernovae. This is a nebulae that we see of gas that's expanding away from a specific point that we can measure up in the sky. And actually, it's a remnant. It's in exactly the same spot as a supernova that was identified by Chinese and Japanese and Korean astrologers in the year 1054. So it was this seen in the night sky by these astrologers in the year 1054. And we can go back with modern telescopes, and this is what's there now. This is the remnant of that famous supernova that Kepler found. If you remember the story of Kepler seeing a new supernova in the sky, this is what that region of the sky looks like now. The gas has been blown out from it. Now, what's left over after the supernovae, again, depends on the mass of the star and what was left over in the heart of this explosion. If the remnant is small, okay, that is, if the star is a little bit smaller than others, the remnant is called a neutron star. It's crazy dense. It's basically as dense as nuclei themselves. So we take something that's more massive than the sun, crunch down into something that's smaller than the island of Manhattan. Right? So it's crazy dense. It basically has the density of nuclear matter. So these neutron stars. Now, the thing that's keeping these neutron stars from collapsing any further is that they're basically nuclei physically pressing on each other with the strong force that's kind of keeping them from collapsing. But if you make the mass of that shell, of that remnant, even bigger than it was, than some certain critical value, there's no known force in nature that can hold back the gravitational collapse, and the thing will collapse into something called a black hole. And a black hole is effectively something that's so dense that there's nothing that can escape its gravitational tug. And so it's possible that when Betelgeuse explodes, at the very heart of that star will be left a remnant that's a black hole. Most likely it'll be a neutron star, but it's possible that it would be a black hole. I'm going to do a whole thing on black holes. I'm not going to talk about them in detail right now. But if you have stars that are more massive than 10 times the sun, and they retain enough mass in their core after their nuclear explosion, they'll make something called a black hole. Black holes are so dense that anything that falls into them can never come out. And that includes light. So one way to think about it is in terms of escape speed. I talked about like the escape speed of the Earth, or launching cannonballs on the Earth, if you remember that. You can think of a black hole as something that has an escape speed that's bigger than the speed of light. So if I take a ball and I throw it up off the Earth, it will come back down. But if I throw it up fast enough, like a rocket, it will escape the Earth's gravitational tug and launch off. If the Earth were more massive, I'd have to launch it at even higher speed for it to leave. But you can imagine a system that's so dense, so massive, that even if you launch something at the speed of light, it would come back down. And so that's sort of that's one way of thinking about what a black hole is. It's so crazy dense that nothing can ever escape its gravitational tug. The existence of black holes are a consequence of Einstein's theory of gravity, which is called general relativity. And I'll discuss that next lecture, a week from today, when I'm going to do a whole lecture on Einstein. And I'll talk about his general relativity in that lecture. So this is sort of a summary of sort of the avenues of what stars can do. A star like the sun will live on the main sequence for a while, eventually build up that helium ash in its core and swell up to a red giant and eat any nearby planets that it's got, and then shed its outer envelope, become a beautiful planetary nebulae until it dies out as a white dwarf. If the star is more massive than that, it has a crazier fate where it will actually explode as a supernovae, and the remnant of the supernovae will be either a neutron star or possibly a black hole. Let's go back to our friend Betelgeuse. Here it is. Okay? Betelgeuse will continue to fuse heavier and heavier elements in its core. We think right now it's fusing helium. So it's done fusing hydrogen. We think it's fusing helium. And it's destined to explode as a supernovae. It actually might explode within the next 1,000 years. If we're really, really lucky, we'll see it. And you probably not, but we might see it. And you might wonder whether you might be lucky if that happens, or maybe not so lucky if that happens. And so it turns out we could figure that out. So what's it going to look like when it blows up? So we can figure this out because we know how bright something should be. of a given luminosity at a given distance, supernovae get as bright as about 10,000 times as bright as the sun. That's pretty bright. You do not want the sun to be 10,000 times brighter than the sun. That will end all life on Earth. Okay? But this thing is 600 light years away. That's pretty far away. So the question is, how bright is it going to be? Well, you can work it out. You can put, I worked this out for you, but you may want to try this. You put in 600 light years for this. You put in 10 to the 10 solar luminosities for the sun here, and you figure out how bright it will be. It turns out it will be about as bright, or probably a little brighter than the full moon. So when this thing blows up, okay, future civilizations living X years from now, 1,000, 5, whatever the answer is, 1,000,000, it'll be bright. And you'll be able to see it in the daytime for a couple months. It'll be that bright. And here's Orion's belt. Here's the sword. Here's Orion's feet. And there's his glowing armpit that will last a little while. And then it will fade out, and then Orion won't have an armpit for a while after that. Okay, have a good long weekend, and we'll see you next week.